In this lecture, we'll talk about the joy of geometry, the oldest of the mathematical sciences. Geometry literally means geometria from the Greek, meaning to measure the earth, right? Geo for earth and metria for measurement. We will learn in this lecture how to measure things like lengths, angles, and areas. Those are the things that geometry concentrates on. The oldest geometry textbook was written by Euclid, who we've met in the past, and he wrote a textbook called The Elements. And The Elements was such a profoundly important textbook that it was used for centuries. Even Abraham Lincoln was said to have learned geometry from Euclid's textbook. It was the first time mathematics had so clearly been spelled out, and the theorems he proved centuries ago are just as true today as they were true thousands of years ago. So we'll begin with looking at the very basic geometric objects. Okay, let's define our vocabulary here. A point is a point. A line is something that goes between 2 points and extends infinitely in both directions. So here's points A and B, and there's the line that goes through A and B. A ray, which is denoted here as OA, you can think of as a ray as, like, say you had a flashlight at O and you pointed it at A, you could look at the line that starts at O and goes through A and indefinitely beyond, but it only moves indefinitely in one direction. A line segment simply starts at A and ends at B. We can draw angles, such as the one shown here. Angle AOB, right, starts with the line segment that goes from A to O and from O to B, and we have an angle there in between. We show two parallel lines. Here's the line AB parallel to the line CD. Parallel lines never meet. All right, and that's denoted by the symbol AB parallel to vertical lines CD. Perpendicular lines, on the other hand, meet, but they meet at a right angle. That is, the angle that it cuts the line into is cut exactly in half. One angle to the left and one angle to the right, and those angles are equal. Those are the right angles. Okay. All of geometry is built from points and lines and come from the following 5 axioms of Euclidean geometry. So I will say them and we will illustrate them. For instance, a straight line segment can be drawn joining any 2 points. Okay, so if you have any 2 points, then you can connect them with a straight line. Right? That's certainly something that we would accept without question, and so that's an axiom that we accept as part of our system. Any line segment can be extended indefinitely. In other words, you can, starting with a segment, you can turn that segment into a ray or into a line. Given any line segment, a circle can be drawn with the segment as the radius and one endpoint as the center. Okay, so here you have a point and you have a radius, and the circle consists of all points that are that same distance from the center of the circle. The 4th axiom says that all right angles are congruent and measure 90 degrees. So anytime you see 2 perpendicular lines meeting, then they're meeting at an angle of 90 degrees. The number 90 is somewhat arbitrary, but that's what we use. The 5th axiom, maybe the most famous of the 5 axioms, says that given a line and a point not on the line, there is exactly one line through the point that's parallel to the original line. Okay, so look at the illustration. You have a line and a point that's not on the line, and there's exactly one parallel line. Not 2 parallel lines, not 100 parallel lines, just one that goes through that point without touching the original line. By the way, that's equivalent to the axiom that any triangle has the sum of its angles always equal to 180 degrees, and we will use that version of the axiom in some of our subsequent proofs. Okay, so here is a simple consequence of our axiom. What are the consequences of the axioms? Essentially, all of geometry can be built from those 5 axioms. Okay, so from this point on, we don't ask you to take anything on faith. You can deduce the theorems with those axioms that we started with. Okay, so here's a theorem. Every straight line has an angle of 180 degrees. How do you get that? Well, let's look at the angle AOB, right? That's a straight line that goes through A and B. Let's bisect that straight line at a right angle. Okay, so there we go from O to C. The line that, by the way, that bisects that line is called a bisector. And now the angle AOB can be obtained by taking the angle AOC plus the angle COB. And since both of those angles were right angles, then the fourth axiom says that each of those angles has 90 degrees. When you sum 90 degrees plus 90 degrees, you get 180 degrees. Okay, let's prove a more interesting theorem. This one's called the vertical angle theorem. Suppose you have 2 lines, AB and CD, and they intersect at some point O. All right, so look at our graphic. We have AOC as one of the angles, the bigger angle, and opposite that, we have the angle DOB on the other side. And the theorem states that angle AOC and angle DOB, or BOD, you could call it either one, that those angles are the same, that there's the same measurement of angle AOC as the angle BOD. All right, let's prove that. We'll prove that by taking a look at some of those smaller angles. That is, if you look at the line AB, we know that the measurement of that angle, of the line that goes from A to B, is 180 degrees. That means that angle AOC plus the angle COB have to sum to 180 degrees. By the way, we call those supplementary angles because they add up to 180 degrees. Similarly, if we look at the line COD, then we see that COB plus BOD, that those angles, since they form a straight line, are also summing to 180 degrees. Okay, now I have 2 algebraic statements. I can now subtract those algebraic equalities to get angle AOC minus angle BOD equals 180 minus 180 is 0. In other words, angle AOC equals angle BOD. So those angles have the same measurement. Here's another nice theorem. This is called the corresponding angle theorem. It says, if you take any parallel lines, let's say line L1 and L2, and you take a line that cuts through both of those angles, okay, as in our picture, then the angle A will have the same measurement as the angle B. Okay, I want to prove that angle A and angle B are equal. Here's the proof. We're going to prove this by drawing a new line in our picture so as to create 2 new right triangles. Okay, so consider that point C up there and cut that line through L2 and L1 so as to form 2 right angles. And now let's look at the triangle on top, that little triangle with angle B, angle C, and that right angle. Now, what do we know to be true about the sum of the angles of any triangle? Well, by Euclid's 5th postulate, the sum of those angles is 180 degrees. So that says angle B plus angle C plus that right angle of 90 degrees is 180 degrees. Likewise, if we look at the big triangle, that is the angle A, the right angle and angle C again, looking at that big triangle, we see the sum of those angles is 180 degrees. That is angle A plus angle C plus 90 is 180 degrees. And now, if we subtract those two equations, what do we see? We see that angle A minus angle B is 0. That is, angle A equals angle B as promised. Here's another famous theorem of geometry. We know that the sum of the angles of any triangle, any three-sided figure, is 180 degrees. But what about larger objects, like four-sided objects? Those are called quadrilaterals or fourgons, right? Five-sided objects could be called fivegons. In general, polygons if you've got many sides. What's the sum of the angles of any four-sided figure? Well, I claim that, and I can prove, that the sum of the angles is 360 degrees. Why is that? Well, look at your four-sided figure, okay, and draw a diagonal from one corner of your quadrilateral to the opposite corner of your quadrilateral. In so doing, you will create two triangles. And those triangles will have angles that sum to 180 degrees, and the other one will sum to 180 degrees. And therefore, when you add up the angles, we're going to get 360 degrees. So any four-sided figure will have a sum of angles equal to 360 degrees. Of course, you might call that a foregone conclusion, but be that as it may. Let's look at a five-sided object now. You've got a pentagon here. I claim the sum of those angles will be 540 degrees. Why? Well, you could chop a little triangle off the top of it, and what you're left with is your fourgon, whose angles sum to 360 degrees. So when you add that extra triangle, now you'll add up to 180 degrees. Or you could take that polygon and split it up into three parts. Each of those parts has angles that sum to 180 degrees. Therefore, when you sum all the angles together, you'll get 540 degrees. And this pattern can be continued. In fact, what you're essentially doing is a proof by induction to show that not only does every three-sided figure have 180 degrees, and every four-sided polygon have a sum of 360, and five-sided polygon have 540, but an n-sided polygon, the sum of the angles will be always a multiple of 180, and it's going to be 180 times the number n minus 2. Okay, here's another important definition used in geometry all the time. The perimeter of an object is the sum of the lengths of its sides. So for instance, a rectangle, which has, let's say, a base of length b and a height of length h, then the perimeter of that rectangle will be 2b plus 2h, because we've got two sides of length b and two sides of length h. The area, we start by defining the area of a square. Right? So that's sort of our basic definition. We'll define the area of a 1 by 1 square to be 1. And once we define area that way, then we attempt to define all areas just in terms of that unit quantity. So for instance, suppose we looked at a rectangle that had a height of 3 and a base length of 4. Then we will define, or actually we can show, that the area of that rectangle is 12, simply by cutting up that rectangle into 12 little 1 by 1 squares, right? You add up the areas of those squares all have area 1. There are 12 of those squares, and so the total area is 12. Therefore, the area of a rectangle with integer sides has an area of b times h, and we'll define that to be the area for any rectangle whose sides have positive lengths. They don't have to be integers. How about the areas of triangles? Rectangles are pretty straightforward. How about the areas of triangles? We will show that the area of any triangle with a base of length b and a height of length h has an area equal to 1/2 BH. In other words, the area of any triangle is 1/2 times the base times the height. Let's prove that. We can prove it easily for right triangles, right? Imagine you have a right triangle with a base of b and a height of h. Why is the area of that 1/2 bh? Well, if we take that triangle and make a copy of that triangle, and let's sort of turn that copy upside down so that now we have a rectangle with a base of b and a height of h. What is the area of that rectangle? Well, we just said the area of that rectangle would be b times h. And since the first triangle and the second triangle had the same area, that says that the area of the first triangle must be 1/2 of b times h. So what we've just shown is that the area of any right triangle will be 1/2 base times height. But it's, to me anyway, it's always been a little bit magical that any triangle will have an area of 1/2 base times height. I mean, just imagine it. Let's imagine you've got two parallel lines, and that first line, we've got 2 points on it, and the distance between those points is b for base. And if those two parallel lines were separated by a distance of h, it says that no matter where you put your third point of your triangle, that the triangle created by the 2 points on the lower line and the 1 point on the upper line, that the area of that is always the same. It's 1/2 base times height. No matter how you slide that point in the top line, all those triangles have the same area. That to me is surprising when you look at it. Let's prove it now. Okay, so here's a triangle, okay, whose base is length b and whose height is h. I'm going to prove that the area of that is 1/2 base times height by doing the following. Let's break up that triangle into two smaller triangles. The triangle on the left will have area A1, and the triangle on the right will have area A2. And now the triangle on the left is a right triangle, and we know for right triangles, the area is going to be 1/2 base times height. Now, if we split the base into two parts, one part of length B1 and the other of length B2, then the area of the left triangle is 1/2 B1 times h. And the area of the triangle on the right will have area 1/2 B2 times h. Therefore, the total area is 1/2 B1h plus 1/2 B2h, and that's equal to 1/2 h times the quantity B1 plus B2. But B1 plus B2 was equal to b, the length of the original base. And so the total area of that triangle is 1/2 b times h. Here's another triangle. You might say, well, that triangle worked, but that was that triangle had a special shape. Suppose your triangle was shaped this way. That argument you gave wouldn't have worked. Well, for that case, where the base angle there is what's called an obtuse angle instead of an acute angle, we can do a different proof. Okay, so here we're looking at the triangle with height h and the base length is b1. And I want to show that the area of that obtuse triangle is 1/2 b1 times h. And the way we'll do that is this time, rather than breaking it into two triangles, we're going to extend it to create a larger right triangle. Okay, so I'm going to extend that line to a line that has length b1 plus b2 so that it connects with that height h to create a larger right triangle. And now we know for right triangles that the area of that is going to be 1/2 the length of its base times the height, right? And the length of its base is b1 plus b2 times the same height, that's h. So the area of the big triangle is 1/2 b1 plus b2 times h. Now the area of the new triangle we created, which I've denoted with area A2, that's got area 1/2 b2 times h because it's a right triangle. Now the original triangle A1 is what you get when you take the big triangle minus the triangle with area A2. And therefore, we take the total area minus the area A2. That's equal to 1/2 b1 plus b2 times h minus 1/2 b2 times h. And algebraically, the 1/2 b2 times h's cancel, and we're left with 1/2 b1h. Now let's look at one of the most famous theorems of geometry. This is known as the Pythagorean theorem that we've met before, but we didn't prove. I just relied on the fact that you might have seen it before. Pythagoras' theorem says that in any right triangle with side lengths A and B, and with hypotenuse length C, the hypotenuse, by the way, is the side that is opposite the right angle. It says that for any right triangle with side lengths A and B and hypotenuse length C, that A squared plus B squared is equal to C squared. Okay? Let's see a proof of this. In fact, I'll show you a proof in a single picture. They say a picture is worth 1,000 words, and this picture appeared in a Hindu scroll over 1,000 years ago. It had this single picture along with the words in Hindi, "Behold," feeling that this picture should say it all, and no further explanation was necessary. Well, you won't get full credit on one of my exams for doing that, so let's give a little extra explanation as to why this proves the Pythagorean theorem. Let's imagine we took our triangle, our right triangle with side lengths A and B and hypotenuse C, and let's adjoin them together to form a big square with side lengths A plus B. Now, in the middle of that square is another square whose side lengths all have length C. How do I know that it's a square that we have in the middle? Well, there are many ways of explaining that. One is that by the symmetry of the object we've created, we see that all of the angles of that four-sided figure have to be equal. And since a four-sided figure has all of its angles adding up to 360 degrees, then all of those angles have to be 90 degrees. Therefore, they are right angles. Now I ask, what is the area of the big square? Okay, the area of that square is A plus B squared, right? On the other hand, we can compute the area of that square by computing the areas of those triangles plus the area of the square in the middle, right? What's the area of each of those right triangles? 1/2 A times B. So when we add up all of those areas, we have 4 times 1/2 A times B, plus the area of that square in the middle. What's the area of the square in the middle? C squared. So when we compare these two quantities, on the one hand, the area of the square is A plus B squared. On the other hand, the area of the square is 2AB plus C squared. So when we set those two quantities equal to each other, we see A squared plus 2AB plus B squared equals 2AB plus C squared. The 2AB's cancel, and we're left with A squared plus B squared equals C squared. Behold. I give that a smiley face also. We can apply the Pythagorean theorem to calculate the length of any line segments. So for instance, suppose I wanted the length of a line segment that, say, went from the point 0, 0 to the point 4, 3. Okay, imagine these 2 points in the plane. And I say, what's the length of the line that connects them? Let's call that length C. Well, if you draw a right triangle that starts at 0, 0 and ends at 4, 3, then Pythagoras will tell you that the length of that line segment will satisfy the Pythagorean theorem. 4 squared plus 3 squared will be C squared. And since C squared has to be 25, then the length of that line has to be 5. And in general, we can show that if you have any point, and we'll use this formula later, that is, if you start with any point 0, 0, and you want to find the length to the point AB, then by drawing the right triangle, the length of the line segment from 0, 0 to AB is equal to the square root of A squared plus B squared. Here's another formula that will come in handy later. If we take any 2 points, not necessarily the point 0, 0, but any 2 points, let's say x1, y1 and x2, y2, and we want to calculate the length of the line that connects them, then by drawing a triangle just like the one we saw before, we can calculate this by looking at this right triangle. The base of that right triangle has length x2 minus x1 by subtracting the x coordinates. The height of that right triangle has height y2 minus y1 by subtracting the y coordinates. And Pythagoras' theorem will say that L squared, L being the length of the line from x1, y1 to x2, y2, is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay, so the length of that line would then be the square root of that quantity. All right, now let's look at a problem that might seem a little challenging. Like, let's say I wanted to create a rope that went from one corner of the room to the opposite corner of the room, say at the other end of the ceiling. Okay, so I start here in the one lower floor and I want to go to the ceiling here. What would the length of that rope have to be? All right, let me put it in more mathematical terms. Let's say I want to calculate the length of a line from the point 0, 0, 0 here in 3 dimensions to the point ABC over here in the 3rd dimension. Here's A, here's B, and way up there is C. Okay? So that sounds like a hard problem, right? We're not in the plane anymore, we're in 3 dimensions. But we can solve this problem by putting it back into the plane. Right? So let's say I drop that point, whoops, back onto the plane. Okay? So instead of looking at the point ABC, let's look at the point AB0. And if we think of the line that goes from 0, 0 to the point AB right here on the plane, we know from what we've calculated before that the length of that line is the square root of a squared plus b squared. But we want to know the length of this line up here, right? Well, can you picture this triangle? We have a triangle now whose base runs across our table here, right? Whose length is square root of a squared plus b squared. And the other side length has length c. So what we're left with is a triangle whose base is length square root of a squared plus b squared, whose height is c. And therefore, all we're really calculating now is the hypotenuse of that triangle. So the length that we're interested in looking at is going to satisfy L squared equals the square of the square root of a squared plus b squared plus c squared. But when you square a square root, the square root goes away and we're left with a squared plus b squared plus c squared. In other words, the length of that line is the square root of a squared plus b squared plus c squared, which is a very attractive looking formula. The length of a line from 0, 0, 0 to ABC is the square root of a squared plus b squared plus c squared. Let's do one more problem. I think this one's a fun one to look at. Imagine I start off with 2 squares, each of length 1, and I put them next to each other. Okay, so each has length 1, and therefore they are 1 by 1 squares with an area of 1. Put them right next to each other. And now I'm going to build on that rectangle to create another square that's 2 by 2. Okay, so look at our graphic here. And now we've created a rectangle that's got two 1 by 1 squares on the bottom and a 2 by 2 square above it. And next to that, we're going to adjoin another square. This will be a 3 by 3 square, right? And above that, we're going to create another square. And what's the dimensions of that square going to be? Well, it's going to be laying on top of our 2 by 2 square and our 3 by 3 square. So it's going to be a 5 by 5 squared. And then we're going to create just one more square over to the right of that. That's going to be an 8 by 8 squared. Now, do you notice the dimensions of those squares? 2 by 2, 3 by 3, 5 by 5, 8 by 8, 2, 3, 5, 8. Who do we appreciate? Fibonacci again. Okay, here's my question to you. What is the area of this rectangle? Well, what are the lengths of the sides of the rectangle? The side on the right has length 8, right? And what's the top length? The length of the line on top. It's 8 plus 5 is 13. So the area of that rectangle is 8 times 13. On the other hand, you could calculate the area of that rectangle by adding up the areas of all the individual squares. So we have a 1 by 1 square, another 1 by 1 square, a 2 by 2, a 3 by 3, a 5 by 5, an 8 by 8. So the sum of those areas is 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared is 8 times 13. It is the product of Fibonacci numbers. And now we've proved a pattern that we saw but didn't prove when we were looking at Fibonacci numbers before. That is, the sum of the squares of the first n Fibonacci numbers is Fn times Fn plus 1. So we've answered a lot of questions about objects with straight lines, but where do we go from here? We could look at lengths of and areas of things like circles, parabolas, and other funny shapes. How do we analyze those? Well, those require trigonometry, calculus, and all of these depend on the magical number pi, which will be the subject of our next lecture.